All right, let's take a look at springs and simple harmonic motion. We're going to start with an idea called Hooke's law. Interesting side note here, Robert Hooke was a contemporary of Isaac Newton, and they didn't particularly care for each other. Hooke had a lot of issues with the science behind Newton's postulates about how the world worked, but that's an entirely different story. Hooke is also famous for his investigations into the behavior of springs. So let's take some stuff that we do know about springs. Well, if we take a spring, and this is my terrible drawing of a spring, and then we add a mass, I think you probably recognize that that spring is now going to be stretched out compared to where it had been before. And it probably also makes sense to you that if you add more mass to the spring, that is going to be stretched even further. So as we add mass to the spring, of course, it's being influenced by the force of gravity. So there is a weight force pulling down on the spring, and that is what is going to stretch the spring out. At the same time that the force of gravity is pulling down, and let's add that in here, there's also going to be a new force that we'll add in there, that we will refer to as the spring force. And orange is a terrible color. Well, it's a great color, but terrible for seeing on this screen. So this is the force that a spring is going to exert on an object. So add that to your repertoire of forces. So the spring would be pulling back. Now, there would be an equilibrium position. If the mass is held in place, the spring force and the force of gravity in this case would be canceling out with each other. If we pull down on that mass, the spring force becomes bigger, and if we push up on the mass, the spring force would become smaller. So essentially, what Hooke found, if we go back to that equilibrium situation, is that the spring force, that force pulling back on the mass, is directly proportional to how far the spring is being stretched. And it's a linear relationship. So if we were to graph the spring force versus the amount of stretch, so delta x, we'll call that, where xo would be here, and x final would be here. And delta x is the amount of stretch that we get. So the more you stretch the spring out, the greater the force is going to get, but it turns out to be a linear relationship if you're dealing with what we call an ideal spring. So ideal springs are essentially the definition of spring that obeys Hooke's law, that as you stretch out a spring, the amount of force the spring pulls back with is going to increase linearly. Not all springs do this perfectly, but within a certain range, most springs come reasonably close to this. Some springs are better than others. And for our class, in order to try to model the situation in as simple of a way as possible, we're going to assume that our springs are acting in an ideal sort of way. Don't get overconsumed with this definition of ideal spring. Just understand that we're going to assume all springs behave like this. And in real life, it does not work out perfectly this way, but it comes close enough. All right? So ultimately, what Hooke then found was a mathematical relationship. And that mathematical relationship simply said the spring force is equal to the spring constant, so there is a constant in the formula, multiplied by the stretch. And so that is Hooke's law. In your lab, you are going to be investigating this relationship, and you are going to be measuring how much stretch you get with a spring, and you're going to measure the spring force by leaving the mass, getting the mass to a point where it's in the equilibrium position. I'll discuss that a little bit further when I do the demos, the video for the lab. But understand, when you're doing Hooke's law, you are looking at the mass on the spring when it's in the equilibrium position. And more specifically, we typically look at this when the spring has a mass on it and everything is at rest. And when it's at rest, you know that all the forces will be balanced. And if we look at our free body diagram, you should be able to calculate how big the spring force is, knowing that all the forces on the y-axis have to add up to 0. So I'll leave that to you to think about a little bit. Now, the next thing we're going to talk about is oscillating springs, but I think I will leave that for later. You should have enough now to complete the lab.